So nice to meet you. Thank you for coming. We are a bit outside of the compiler world. We are from the security world. We are security researcher in a consulting company, and we found basically the LLVM project very useful from some internal development we've been doing. And what we want to present to you today is what we've been capable of doing with the LLVM project and give you some feedback on this adventure. So quickly, I'll recap what is instrumentation. I think many of you already know what instrumentation is, but the easiest way to summarize that you want to transform a program into its own measurement tool. So it's become an instrument that is capable of observing any state of the program at any time during the execution. And once you have that, you want to automate the data collection and processing of data so you can do automated analysis on those data. And as a quick note, we know there is a lot of wonderful LLVM-based static instrumentation projects and framework. However, in our field, it's very rare we get the source code, so we always have to work on the binary. So why would you want to instrument a binary? Well, the first obvious answer is to find memory bugs. I'm sure many of you have used Volgrind, and it's a dynamic binary instrumentation framework. What it does is that it's going to hook all the allocator, track all the memory allocation, the allocation, and then instrument the binary so that each time there is a memory access, it can detect out-of-bound access and things like that. Another use case is for fuzzing. The guy earlier in the other room was talking about fuzzing, and the first thing you want when you fuzz a binary is that you want to get some feedback on how the binary is reacting to your test case. And so you want to measure metrics like code coverage. But you can go even further and you can try to build a symbolic representation of what's happening in the code so you're better able to explore new branch paths and have test cases that do many more things than the previous ones. And that's also a field where you need some sort of instrumentation. And the last one is recording execution traces. So a very good application that's been quite popular recently is timeless debugging, where you can replay what's happening in the program backward and forward. But what we've also been working on are software side channel attacks against cryptography. So where you are able to mount side channel attacks, but against software implementation of cryptographic primitive. So a question we often get when we present this is, why are you not using debuggers? And briefly, the problem is that debuggers are extremely slow. So as a quick recap, that's what's happening in a debugger when you try to continue after a breakpoint, is that your debugger will send a resume system call to the kernel, and then the kernel will reschedule the target for execution. And once the target hit the breakpoint, you have a trap interrupt that goes back to the kernel, and then the kernel has to do the dispatching of the signal to signal back to your debugger and reschedule its execution. So while it's acceptable for human, if you want to automatize this kind of process, it becomes very slow. So the only logical answer is that you have to get rid of the kernel in the middle. And well, you could do that bare metal, but that's not very fun. So the easiest solution is to try to run your instrumentation, your measurement code, inside the target itself. So you want somehow to mix those two blue processes. And basically, this is what dynamic binary instrumentation allows you to do. So there's a few existing frameworks when we started working on this project, and we've used many of them. So the earliest one is Volgrind, which was released in the year 2000. It's open source, it's GPL v2. However, the design makes it extremely limited to POSIX systems. So it's, well, they've said that they would never port it to Windows. It's cross-architecture because they rely on VEX, which is an intermediate representation where they implemented many architecture. And when a user tries to instrument a program, he has some abstraction of of his instrumentation process via this VEX layer. So he can actually think about it in terms of IR. Of course, the problem is then you have to write instrumentation in an intermediate language that you don't really know, and that is not that well documented. So this is a bit complex. And however, in terms of modularity, and we'll come back to that later, it's monolithic. It implements everything. It implements a loader, a signal handler, thread scheduling capabilities, and it's difficult to use Volgrind and inject it into another process, for example. A second popular framework is Dynamo Rio, which is 2002. It's BSD licensed. It's nearly cross-platform. It weirdly doesn't have Darwin, so macOS and iOS support. It is kind of cross-architecture. The problem is that they are trying to re-implement everything by hand. So if they need to implement a new architecture, they will start with the disassembler, and this takes time. I'm sure many of you guys know. And the other problem is that it doesn't really have an instrumentation abstraction. So what they offer users to do is to do raw instruction manipulation. And well, if you don't know low-level code, it can be difficult. The last one is Intel Pin, which is quite nice. Unfortunately, it's proprietary, but it's very easy to use, and but it's also limited to Intel platforms. So briefly, what a DBI framework does is that it's going to try to insert the instrumentation at runtime inside the code. So roughly, it looks like this. Is that you have your original binary code, you disassemble it, you analyze it, generate instrumentation, and try to insert new code and then execute it. Of course, it cannot work that simply, and you have many problems. The first one is disassembling. In a binary, when there is no debug symbol, debug information, you cannot just disassemble the whole binary. You don't know where the code is. So it's not possible to disassemble everything, do this process in advance. What you need to do is discover the code as you go. So it works a bit, well, we'll talk about it later. The second problem is, the solution is code discovery. So basically what you do is that you're going to execute your program piece by piece, so basic block by basic block, and then you can discover where each basic block goes. And this gives you the information. You can disassemble and instrument your binary piece by piece at runtime. And basically this forms a short execution cycle that really looks a bit like a just-in-time engine. The other problem is that you don't have a free space in your binary. You cannot just simply insert instrumentation because there is already things in place, and compilers are quite good at saving space where they can. So yes, if you want to insert instrumentation, you need to find some place to do that. So you cannot do that in place, so the only solution is that to do that somewhere else. So you want to allocate new executable pages and relocate your original binary into those pages. So yeah, I will skip why we need to relocate. I think you guys know that, but you have relative reference to memory addresses, and if you move the code, well, those becomes invalid. So you need to completely rewrite the code to fix those references. And we refer that inside our engine as patching. So if you summarize everything, this is the cycle of life of a DBI. It's a short execution cycle where you disassemble your binary piece by piece, basic block by basic block, you patch the basic block, you add instrumentation, you reassemble it into an executable page, and then you execute that page. And then you look at where that page, well, the control flow is going next, and you disassemble the next basic block.
Okay, thank you, Shar. So we have seen like the basic principle of what a DBI is. Let's have a look of how we can design our own. I'm sure you are also familiar with this. So basically, a software is instructions. These instructions, they are grouped in blocks, they're called basic blocks. And these basic blocks, they are linked together using branch instruction. And this is what we are calling a control flow. And basically, with a DBI, what we want is something like an under control flow, where, in fact, between the execution of two blocks, you want to call back your own code, your instrumentation code, the code of the DBI. So you are like splitting between a guest which will be like the original basic block, and your host, which will be your instrumentation code. Yeah, by control, I mean, a DBI is like about keeping control of the execution. For this, you need to do two things. You need to modify the original instruction, of course, to take this control. But what you don't want is to modify the behavior of a program, because if you do it, I mean, you will probably crash or have invalid results. So you need to be very careful about how you are modifying the original instruction. So what do we need for this? Basically, we need a multi-architecture disassembler and an assembler, but also some kind of intermediate representation to work on and to be able to apply our transformation modification on. But the fact is that we don't have like unlimited resources, so we don't want to implement a multi-architecture disassembler and assembler. And we don't want at all to abstract like every instruction semantic, because it means like parsing all the developer manual of your CPU. And I kind of like them, but it's not that fun to take like 1,000 instructions and rewrite the microcode in your own representation. But things have changed recently. I mean, recently, since a while, with LLVM. And LLVM, like for you guys from compiler, it's like evident, but from security, LLVM was quite unknown for a long time. And when people realized it was there, it was like a miracle. Because, yeah, basically LLVM has everything. It supports already all the major architecture, I mean the one that matter for security guys, because it's the architecture that are used. It provides, of course, a disassembler and an assembler. And also, the thing is very interesting is that this assembler and disassembler, they all work with the same representation. And this representation is LLVM matching code. So let's have a look very briefly. What is very nice with matching code is that it's a minimalist layer with very simple structure that are totally generic, but still encode enough information to work on. But the thing is that it's generic, but because of some heavy compromise, and we will see how it can be a problem for us. So in a DBI, basically what you want to do, it's like creating some new instruction. And if we have a look here, the thing is that with MC, every instruction, they are using the same representation, so MC structures, but every time in a bit different way. For example, this move will be encoded like this. And if you take another instruction, it will be encoded in another one. And like the MC operand, the way they are used, it's not particularly easy to write it. And so creating instruction can come very painful if you are writing the structures by hand. Also, you will need to modify instruction. And for example, a branch instruction, if you want to take control back, you need to modify it. This is like the MC-inst representation of a jump, very simple one. But if you want to patch it, let's say for jumping from an address contained in a memory, yeah, it's becoming, again, a bit more complex with its own representation. At the end, we will want to apply patches. And so let's have a look at this very simple example. Why do we want to modify this instruction? Because we will relocate this instruction in memory, and you see that this instruction uses a relative address based on the instruction address. And so if you want to patch this to relocate somewhere else, you will need to use tricks. Like you will force to replace, for example, the original RIP register by another one, which will contain the address, the original address of the original instruction. But as you can see, we are erasing the RBX register, so you will need to first backup it somewhere, and yeah, of course, restoring it later. And as you can see, things are becoming more complex here because we are adding instruction, modifying some. And as we have seen, this encoding, they can make these things very painful, especially if your patches are complex. So this one was very simple, but you can have very complex patches very quickly. And we can see also that some of these transformations, they are composed of generic steps. I mean, like backupping a register, this is something that you will do like every time. So yeah, basically we need abstractions to avoid a bit of this pain. And we need to create some engine, like a patch engine, that will take an MC instruction and will generate one or more with our patch applying on. For this, we had an idea, which was, okay, basically, what if we are able to identify the transformation steps that you need to modify and patch the instruction, and to regroup them in some kind of language, but some kind of domain-specific language. And the idea was, okay, the instructions are architecture-specific, but maybe this DSL could be generic. So it could describe the transformation on the MC inst level in a generic way. So yeah, we get some inspiration, and we have been able to formalize it a bit. And let's have a look. I will not have time to describe it in details, but we will just get an example with the temp here. So if we get our previous example, basically what we want here is to get a temporary register that we can use for something else, here for storing the original address of the instruction. So we will want to generate this, like a backup, setting a value, and then restoring the register. And from this, with our language, basically it will be just a temporary. And this temporary will be identified by an index, so we will be able to work on later. And by working on, I mean, yeah, basically when we want to modify the original instruction, we can just use the language. So we reference our temporary here, and we also say, okay, we want to replace, we substitute the original PC, so the original RIP register, with the register from our temporary. And we don't have to deal with all this, all the creation, and we don't have to select which register we can use, which one is free, because it's handled by the engine. Also, the idea we had was, okay, this modification, basically there are rules. There are rules because they are composed of one or more conditions. When you want to, if you want to patch an instruction, it's because there is a reason, like the use of an RAP register. But these rules, it's also composed of actions, the modification that we will apply on your instruction. And basically, this is an example which is taken from the source code of the DBI, and this is a rule which do the patch that we have seen before. So the rule, the condition is, okay, my instruction is just using the RIP PC register, and then we can, using like the keywords of the language, just do all the modification in an high-level way. Like doing this, we can support an architecture by just adding rules and rules and rules and rules. So the lesson we learn, yeah, LLVM is just very robust for modifying binary code. And even if MC is a bit difficult to work on, we have been able to add this abstraction. But the thing is, they are kind of hard to conceptualize. I mean, we took lots of time to think about this language, and honestly, it's not perfect yet, but yeah, I mean, it works.
So yeah, second part that is important is the DBI, is context switching, because basically you end up in a same process where you actually have two entities, two different contexts. We like to refer them from with the virtual machine terminology, the host and the guest. So the guest is the original binary, and the host is the DBI engine and the instrumentation tool, and they generate the instrumented code that also runs into the guest context. And they share the same memory and the same CPU context, and you need to switch between those two contexts at every cycle quite fast. But you don't have any help from the kernel or the CPU, because from the kernel you're the same process, but for the CPU you don't have any privilege to access like virtualization extension or anything. So you need to do that by hand. So you need by hand to save and restore CPU context from guest to host and vice versa each time you switch. However, you want to avoid any side effect on the guest. It's simple to push value on the stack, but maybe it's a well-formed C program, and we can assume that it's not touching the top of the thing above the stack for him. But maybe it's not a C program, maybe it's a more esoteric language, and maybe it was written in assembly, or maybe there's not even a stack at this point in the process. So we cannot really use the stack for that. We cannot either erase a register, because any register we erase, we are not able to recover. So basically, we need to be able in one instruction to load and store memory, and the only way to some part of memory we control that the guest is not aware of. And the only way to do that is with relative addressing. And so we need to be able to do relative addressing from the guest code to some host memory. The problem is that it's very easy in the x86 where you get a 32-bit offset, and it's wonderful. However, most architecture, especially RISC architecture, have a lot more constraints in the size of the offsets you can use to access and do relative memory addressing. And so, for example, on the ARM, you're limited only to 4096 byte of offset. So we need, the only solution is that we really need the host memory next to the guest code. And also we have a problem is that we want to play nice with data execution prevention and other security feature from kernel that tend to dislike read-write executable page. So we really want two different pages. So one read execute and one read write. So our solution basically looks like this. So we are allocating two pages. The first one we call the code block, which is read execute, where we can store and execute code. And second one, the data block, which is read write, where we can store our data. And so you see at the top, you have the prologue, which is the context switch from the host to the guest. And that can rely to relative memory address to the guest context and the host context to do the storing and restoring of registers. And then inside of there, we can store different basic blocks, and we also have an epilogue where we do the inverse context switch. And we also have a solution with a selector that allows us to basically program the prologue to tell him where we want to jump next without having to modify the code, change the permission on the read execute page. And we also have some space at the end. I'll briefly mention that later. For constant and shadow variables.
So yes, the thing is like this exec block, you will need to basically emitting it in memory, and by emitting I mean you will need to ascend the code. And so we need some kind of like the LLVM machine code JIT engine, but we have to keep in mind that our layout, the layout of this exec block is custom. So we don't have things like modules or function. We have very specific prologues and epilogues used for the context switch. We have some tricks like a selector which allow us to store more blocks inside one exec block. And also all the data, they are handled in a very particular way. So when thinking about it, we know that LLVM has already several JIT engine. By JIT engine, I mean the MC JIT engine. They are honestly very well designed. But the thing is that none of them fitted our strict constraint. But LLVM basically provides everything that is needed to create a new one, which is like they have cross-platform memory and management abstractions, and also, of course, the powerful in-memory assembler of the LLVM MC. So yeah, basically LLVM is just perfect. One thing we need really to keep in mind that when you are designing a JIT engine for a DBI, it's kind of hard. And what is very easily to mess is that to be locked down on a particular CPU architecture. And for this, really, portability need to be taken like from scratch, from the beginning of your project. You need to for the first proof of concept, to try on several architecture if your RD will work.
So now I'll talk a bit about the instrumentation process. So basically, you want to abstract in some way to the users how the user of your framework, how we can manipulate a binary. And you have two ways to do that. The first one, it's the easiest one, is to simply offer him the possibility to have callbacks on specific execution event. For example, new instructions or new memory access. It's very easy, but it's quite low performance because each time you do those callbacks, you have to switch context back and forth between the host and the guest. So if you switch context at every instruction, it's, well, it's kind of slow. It's still faster than a debugger though. The other one is to add inline assembly code. But then it's very difficult for the user because he needs to understand the assembly code he needs to write and understand the side effect he has on the instrumentation process and things like that. And so it's quite hard to use, but you can get very high performance because you avoid the context switch. And also inline assembly code can be seen as a superset because it also allows you to trigger callbacks. You can write assembly code that call callbacks and trigger the context switch. So what we decided to do is to reuse our patch DSL to do both of them, to basically do inline instrumentation and then have abstraction on top of it to allow callbacks. Another thing is that you want to provide an easy-to-use API to your user, and the first thing he will have when he's in his instrumentation tool, the first question he will have is, tell me more about the code. Like, what is the instruction I'm on? What's the mnemonic? Can you disassemble it for me? What are the operands? Is it a register? What's the side of the register? Is this instruction doing memory access? And this is all a lot of information you have to provide to the users. And the last one, memory access, is particularly difficult to provide. And so we'll just focus on this one, is that we have a mechanism to do inline instrumentation of the binary to record memory access and then offer them to the users. So basically, if you want to do inline instrumentation of an instruction to get memory access informations, you have three problems. The first one is to identify the instruction that's making memory accesses. The second one is evaluating access, address, and value at runtime. And the third one is reporting this information to the instrumentation tools. And for the third one, the solution is easy. I showed you that the exec block in our data block, we had some space left at the end, and we use that for basically instruction shadow variables. So each instruction can allocate variable and store information about its execution, like the address of the access it made and the value. And for the first two, the question is, can you use LLVM MC for that? And our answer is yes, kind of. And the problem is that MC is very generic and it lacks a lot of architecture-specific details. And sometimes the information is there, it's present, but very hard to obtain. For example, register size. You have to go through a few LLVM class and instance before getting that information. Sometimes the information is present, but it's incomplete from our point of view. Things like LLVM doesn't say that a call does a store because it stores the return address on the stack. And for us, it's a store, we care about it. But I guess when you're writing compilers, of course, you know your call is going to store the return value on your stack, and so you don't tell it. So if you ask MC if it's doing a store, it tells you no. Or also implicit registers, not all MC instructions are completely modeled in terms of side effects. And sometimes also the information is simply not there. For one thing that we really liked is memory access classes and semantics. So from instructions, how is it accessing memory? And so what we would like is to enhance MC, and it's one of the reasons we came here, is that we worked around some of those issues with our own custom table next to the table gen tables. And that this kind of information from people from the security scene or the reverse engineering scene and binary analysis is very useful for us. And if it were there in the first place, it would be a very awesome tool for those people. And we kind of think it has this place because there is this MC as a hub philosophy where MC is supposed to connect a lot of different tools together. And yeah, we are open to discussion, and we would love to contribute to those layers, but we don't really know LLVM people well enough and how they see those issues. And so if you're working on those layers, please come talk to us later.
So yeah, everything we discussed, it's implemented in an open source tool, which is QBDI. Yeah, the name is not particularly original because it's Quarkslab Dynamic Instrumentation Framework. It's cross-platform, as we said, because today we don't have choice in reverse engineering. We need to support all the platform. And we've really focused it to be user-friendly. So there is easy-to-use C and C++ API, an extensive documentation, of course, and binary packages. One thing is that we really care, you've seen that with all the previous framework, there was an issue with the modularity. I mean, it was like complex package when it was very difficult to just do what you want with it. And if you had like weird ID, and people in reverse engineering, they have weird IDs, it was a problem. So really care about having some design which is modular. And by modular, we mean we can inject this framework in the memory of any process. We are free to link it with another library, for example, if you want some tricks at an higher level. So yeah, it was very important for us. So yeah, it's available on GitHub. Yes, if you are interested, just give it a try. Maybe we have like 1 minute for a demo. Yeah? So we'll try a demo. Oops. So for this kind of tools, I don't know if I am able to mess like all my demo. It's some crazy shit. Like I prepare the demo every time, and when the time comes, it's never ready, but okay. So as you can think, an instrumentation tool like a DBI is not very, it's very difficult to showcase because it's like a framework. But we'll just have a look with one test code. So we have also Python framework. And this Python framework allows us to very easily write any instrumentation tool with the DBI. So this one is just, it will start at the beginning of the execution, and they will add callback for each basic block executed, and it will store the history in a file. So if you execute it, we can just do this. So we just call QBDI with the coverage tool, the instrumentation tool, and we will use like any random binary like this one. And so what we created is this. We just created a coverage file, which contains like things like the loaded libraries and all the basic blocks that have been taken. And this file, basically, we can load it inside like a tool, which is not working. Okay, yes, thank you. So if you are launching the IDA tool, which is a disassembler used by reverse engineering people, yeah. Okay, so we will just load it. It's very small on one screen, very big on another one. It's kind of weird for me, but I hope I will manage. So here we will just launch the analysis of the binary. It's a very small one, so it's very fast. And what we can do right now is just load these traces. I mean, load these traces. Okay, here. Basically, using and we can see, so the traces is recognized by the tool. And if we take, for example, this function, we have like the code coverage of the execution we just done. So like everything is blue is the basic block that have been executed. Yeah, so basically it works. So thank you very much. If you have any question.
First, I have a little bit of a probably clarification, because it seems the statement about the wall grind wasn't entirely correct, in the sense that it neither bound to POSIX, it does work on macOS, and it is modular because it actually have multiple like front ends tools, what they call it. It's like they have a cache grind and a few other tools. So as
which tool are you talking?
wall grind.
We never said that it was not working on macOS because macOS is POSIX.
Yes.
So Valgrind is already working. It was Dynamo Rio has more difficulty with macOS.
Okay. So
what we meant by modularity is mostly the fact that, for example, Valgrind, if you try, you cannot use an external library inside your instrumentations because you have a lot of limitation regarding to that, or it's very difficult to disable thing like thread scheduling or the signal stack handling by Valgrind. So this is what I mean. One of the things we do, for example, is that we're able to use a FRIDA to inject with FRIDA inside a remote binary and integrate with this framework and route call and instrumentation between our DBI and JavaScript instrumentation functions.
Well, one of the idea of the DBI basically was compared to other framework, instead of forbidding for sometimes bad things like instrumenting the lib system library, because you can mess things because you are doing everything inside the same memory. So some DBI project, they say, no, you will not be able to do this. Basically, we say, okay, you will be able to do this, but we will provide tools for you to make it in a safe way. I mean, safe way, like when you do base jumping, but...
okay, just was like clarification, because it may be misunderstood. Yeah. I understand that you know how Valgrind looked because you probably evaluated, but actually the actual question was, it seems from your instrumented code, it looks like it's not really working well with the threading because you use like RIP relative spill slots, so it doesn't seem to work with with actual concurrent code. And your code it uses RIP relative locations for spinning, which means it will not work if the same code will be executed concurrently on multiple threads. Because the same slot will be reused for different values.
No. So this is our approach is that if indeed have to execute on multiple threads the same code, then they simply have the different translation in different part of the memory.
But if it's this, so for different like stack point, you have different translations?
Yes.
Oh, okay.
Yeah.
It's part of the compromise we have made. Like for example, if you want to instrument multiple thread, you will have just one instance per thread. It's like everything has been made with compromises, and that's why that it's different from the other one. I mean,
and actually, it was also the comment, and the question was, why don't you use QEMU in that solution? Because actually, like QEMU, especially if used in user mode translation, it does exactly what you need. It has a decoder. You could put an arbitrary instrumentation in IR, and it has a code generator.
Yeah, QEMU is working a bit like Valgrind. Yeah, it's TCG, which is another. Like it's comparable to VEX. And basically what they are doing is that they are disassembling everything, translating them inside an intermediate representation, like every single instruction inside this representation, and then they can apply transformation on it and reassemble them.
What you also lack with those kind of things is that you, as I said, you don't have an API to really get information from the code. QEMU was not made for that in the first place. So, for example, you have to load another disassembler if in your tool you want to get this information. Oh yeah, we could.
Maybe it would be good to discuss this later. With time, we have maybe one more.
Yeah, quick question. So what's a typical slowdown you see of the instrumented binaries?
It's basically the performances also are not one of the focus, but performances are quite good because basically what is very slow, it's the creation of an execution block. But after what we couldn't describe here, that we are using caches. So after the creation of a basic block, it's inserted in a cache. So on the next execution, the basic block is just taken as it is and just re-executed. So the slowdown is basically about, like, if you don't add instrumentation tools, the slowdown will be the context switches, of course. But the thing is that we worked a lot with other tools, and like in lots of cases, the slowdown is not because of the DBI, it's because of the instrumentation tools that you are writing on top. So at the moment, I just say, okay, there is lots of limitation for some tools because they focused on performances, and for like lots of use cases, I don't very care about on these performances, or I don't care in the same way. Because like, for example, with SDBI, we are doing fuzzing, and with very decent performances, compared, for example, to using Unicorn, which is based on QEMU. It's just because it's designed for some specific application, and that's why it's good to have a lots of different tools. If like every tool has its strongness and its weakness, so yeah, we just design it in a bit different way compared to other tools, and it was to be able to have an advantage on some very specific use case.
Okay, thank you. Let's thank the speaker again.
Thank you.